talk about waves. This is a nice long unit, and there's going to be plenty of properties we're going to cover. So today we'll just deal with the most basic properties and the most simple equations, and obviously we'll progress in difficulty as we move along. So the first thing we need to do is define exactly what a wave is, and we're going to define wave as a disturbance or vibration that carries energy from one point to another, but does not carry matter. If you watch any sci-fi, there's certainly ideas of transporters that replicate your matter and transmit the information, and then you have the equal pattern on the other side. They still didn't deal with transfer of matter, though. That's something that, to this point in time, is still very science fiction. Where would we see waves? Well, we'd see them in a whole bunch of different cases. Here's 4 examples right here, different examples. At the bottom right there, you see the traffic light, and that's your basic visible light. Top right there, now we're dealing with sound waves, which propagate through a medium by compressing the air around it. In the top left there, you see a radio wave, which isn't to be confused with a sound wave, because radio wave is actually part of the electromagnetic spectrum, which is, again, the spectrum of light. And finally, in the bottom left, the waves we'll be dealing with quite a bit today, this idea of mechanical waves. So in dealing with mechanical waves, we're really going to talk about 3 different types, and the way we're going to be able to tell the difference is the way they look to the observer. The first one here is a transverse wave, and what's going to happen is this particle is going to vibrate up and down perpendicular to the direction of the wave. So you can see on this macro here that the particles are actually moving up and down. It looks like a wave as you know it. Light works like this, and so does something like a vibrating guitar string. There's also this idea of longitudinal wave, where particles of the medium move parallel to the direction of the wave. So instead of moving up and down, it's actually vibrating left to right. And the best example of this is the idea of sound. As I said, it propagates through a medium, and when it does so, it actually compresses the air and it moves along almost like a snake moving across the ground. And finally, our third one is this idea of surface waves, and really what they are is it's a mixture of transverse and longitudinal waves. And you can see here in the diagram that if you add more transverse waves, your resulting surface wave gets more and more complex. And to be quite honest, this is way more complicated than what we're going to deal with this year. So I thought you should realize that they exist, and that the ocean is a little more than just a simple longitudinal or transverse wave. So when dealing with waves, we're going to talk about certain properties that we're going to need to label and understand at all times. So what I'm going to do is I'm going to draw a wave front, and it's going to be a transverse wave, and it is going to be theoretically as consistent as we can. Perfect. Well, the white box that this wave is in is called the medium, and it's really what the wave travels through. When we talk about the speed of light waves, we base that upon its speed through a vacuum. That would be a medium, as opposed to going through air or water or something more dense or less dense. Another idea is this idea of the crest. Well, the crest is this point right there, and it's the high point on the wave. Obviously, there's more than one crest because this is a repetitive function. So certainly this is a crest here and that's a crest there. In comparison, the low point here, that down there, is called the trough, and it's just the lowest point on the wave, and it's fairly simple to identify what that is. When we're talking about physical properties of this wave, we're going to talk about the amplitude, and that's the actual displacement from rest. Rest is this initial line that I drew, and the amplitude is the distance from that line to the crest or trough. And you'll notice how I've labeled them all the same, because they are supposed to be the same unless there is some kind of dampening field involved that could actually shrink the wave front as a function of time. So we don't need to worry about that. We're going to deal with nice uniform waves in this case. And finally, we have wavelength, which we're going to label with the Greek letter lambda. And what that means is it's the actual distance between two crests or troughs in our case. So we have one crest and one crest, the distance in between, that's our lambda. And if we looked at the next two crests, that too is lambda, because it should be consistent if it's a uniform wave. The same thing holds true with the troughs. You can get lambda that way. In general, you want to go from a point to when the wave repeats itself, that next point, the distance in between, is your wavelength. So if we take a look at this point here and that point there, that distance in between is also lambda. So there's many different ways for you to find wavelength. So these physical properties, this idea of amplitude and wavelength, they're going to help us identify waves and what type of wave they are and how much energy they have and perhaps even what its velocity is. And in order to do that, we need to start coming up with some mathematical relationships to connect these ideas. So, period, by definition, is the time it takes for one complete cycle of a wave to complete. You'll remember that when we measured wavelength, we measured it from crest to crest or from trough to trough. Well, that time that it takes to get from that one crest to the second crest, there's your period. Conversely, frequency is the number of complete cycles per second measured in hertz. So there is a big difference here. The period is how long it takes to complete one cycle. The frequency is how many cycles will it complete in 1 second. You've probably heard about things like gigahertz when we're dealing with cell phones, or megahertz when we're dealing with radios. These mean that in 1 second, the wave will actually go up and down 1 billion times. It's an obscenely fast amount. Well, these two quantities are actually related to each other with a reciprocal function. And the frequency is actually equal to 1 over the period. And this shouldn't be overly surprising, because if you take a look at the units of frequency, you'll notice that they're in cycles per second. And if we go 1 over cycles per second, we'll get seconds per cycle, which is exactly what our definition of period suggests. It's how many seconds it takes to complete a cycle. So these two are reciprocal to each other. So let's take a look at a question where we might be able to use this. Playing middle C on a piano produces a sound with a frequency of 256 hertz. What is the period of the sound wave? So again, I want to remind you that a hertz is equal to cycles per second. So if we take the inverse of that, we're going to get seconds per cycle, which will be the period. So we simply use frequency is equal to 1 over period. Solve for period. Period is equal to 1 over frequency. Let's put in the value, 1 over 256 hertz, and you're going to end up with 0.00391 seconds. So an incredibly fast period. Now, one thing I'm going to point out is the idea that hertz can use the prefixes just like distances and times and whatnot. So watch out for gigas and megas, because if those are the case, this wouldn't just be 256, it'd be 256 times 10 to the whichever value we're looking for. But in this case, it's a rather straightforward calculation. Let's try something a little different. Well, if you remember that our equation for speed in kinematics is velocity equals distance over time. This is in uniform motion with no acceleration, which again, with waves, the only thing that's going to affect the wave's speed is the medium that it travels through. So we've defined some things now. We've said that within a wave, the distance that a wave travels is really one wavelength, and the time that it travels is equal to its period, which is 1 over the frequency. Well, if we take these two ideas and we plug them into this equation, what we end up with is one of the more useful equations that we're going to deal with this unit, and that's the idea of the universal wave equation. And its form is V is equal to lambda F, where in this case V is our wave speed in meters per second, lambda is our wavelength in meters, and F is our frequency in hertz. And don't forget hertz. Cycles per second, well, that's also equal to 1 over second, because cycles has no actual quantified unit. Let's deal with another example. Let's say that an air horn sounds at a frequency of 220 hertz and are incredibly bloody loud. If the speed of sound in air is 330 meters per second, what is the wavelength of the sound wave? Okay, well, we have a velocity and we have a frequency, but we need the wavelength. As soon as you hear that, let's do V equals F lambda. And let's solve for lambda. So lambda equals v over f, which equals 330 meters per second divided by 220 hertz. And that's going to give us an answer of 1.5 meters. So again, all the units were just nice and easy, so we can just plug and chug. Let's try one more, and then I'll send you on your way. Let's say that the distance between successive crests in a series of water waves is 4 meters, and the crests travel 8.6 meters in 5 seconds. I want you to calculate the frequency of the block of wood bobbing up and down on those water waves. So let's take a look at what this picture looks like. We have a wave. And we know that there is some kind of block sitting on the wave. And we know that the distance between successive crests is 4 meters. Well, what does that also mean? That means lambda is equal to 4 meters. And we're told other things. We're told that the crests travel 8.6 meters in 5 seconds. Well, this distance here then is 8.6 meters. And it travels that distance in t equals 5 seconds. Well, we were able to derive the universal wave equation using v equals distance over time. And wouldn't you know it, you can also use that in this case, because these two quantities mean that velocity is equal to distance over time, which is equal to 8.6 meters over 5 seconds, which is going to give you a velocity of 1.72 meters per second. Well, why did we calculate that? Because we know that v equals f lambda. We're trying to find the frequency, so let's solve for f. F equals v over lambda. Now we can plug in this velocity. We already know the wavelength. So 1.72 meters per second divided by 4 meters, well, that's going to give us a final frequency of 0.43 hertz. So there we have it. So in this case, we were able to use a little uniform kinematics as well as our new universal wave equation, and from that we could actually find out just how often it's bobbing up and down. So it only goes through 0.43 cycles per second. So there you go, my friends. We've got the beginnings of an understanding of what waves are all about. We've talked about 3 different types of mechanical waves. We've talked about a couple equations. Super important stuff. Get to those questions, and we'll see you again.